morning, all of you. Thank you, Dr. Stephen Chakravarti, for inviting me in this Indo-French seminar on robust knowledge. So we all know that quad rotor is used in military, civilian, commercial applications, civilian private applications also. Like we know that nowadays in marriages also people use quad rotor for videography, photography. We know that it has application in the military for surveillance. So needless to say that it has application, and we can see that nowadays it has been used in agriculture, infrastructure inspection, and quad rotor have been extensively used for these applications due to this mechanical design and reliability. So if I will talk about the system description, you can look at this figure over here, which basically tells you that quad rotor is a 4-rotor copter with 6 degrees of freedom and 4 actuators. I'll tell you what are these 4 degrees of freedom and the actuators. And you can see over here, basically these are 4 rotors mounted on a fixed frame, and each rotor is powered by independent motors. Okay, and then if we look at the dynamics of this quad rotor, it is actually under actuated dynamics. That I'll explain in my next slide. And we will also look at that the structure of the dynamics of the dynamics of quad rotor is highly coupled, okay? Because each state is coupled with other state in the nonlinear terms. So, and it is also a multi-input and multi-output system. And the quad rotor can be designed in different sizes, depending on the application. So you might have seen very big drones for the military applications, and you might have also heard of crazy flies, which are like small drones, palm size, which can be used to basically see the application of any simple controller, if it works or not. Because what I say that dealing with a big quad rotor can be dangerous at sometimes. So just to check the applications are controlled, we can actually do the control of a crazy fly. So it comes in different sizes basically. And of course, as the small size, it has become safer, but the control of those kind of quad rotor becomes difficult because they are small in size, so they have more maneuverability, so the controller becomes difficult. So this is the mathematical model of a quad rotor developed using Newton-Euler formalization. So here basically the translation and rotational motions are combined to represent the dynamics of a quad rotor. You can see over here we have these states x, y, z, which is nothing but the position in the inertial frame. So we have to look at the key frames. One is the inertial frame with respect to which we will be measuring the distance, and then we have a body frame which is the frame of the quad rotor, and so these x, y, z are the position in the inertial frame. Then we have these angles phi, theta, psi, which are the roll pitch and yaw angle, and they are in the body frame, and we have basically put these constraints or these angles that phi is between minus pi to pi by 2, theta is between minus pi to pi by 2, and psi is from minus pi to pi. So just keeping in mind that phi represents the roll angle, theta represents the pitch angle, and psi represents the yaw angle. And you can see there are 3 more differential equations over here. These are basically P, Q, R. These are the body angular rates. So as I was telling you, we have 2 frames, the inertial frame and the body frame. So this P, Q, R are the angular rates in the body frame. And this equation number 2 basically gives a relationship between the angular rate in the body frame and the phi, theta, psi in the inertial frame. And of course, we have this Jx, Jy, Jz, which are the moment of inertia around x, y, and z axis. So given this system dynamics of a quad rotor, if we do a small angle approximation, where basically we assume that the quad rotor has to track up, a path which is not having a high angle maneuverability. So if we do that kind of approximation, we can basically write these differential equations in this 6 second order differential equations. And here you can see basically these 3 second order differential equations are obtained by this small angle approximation, because when you will have phi, theta, psi as small angles, this becomes phi dot becomes P, theta dot becomes Q and psi dot becomes R. So from there, by substituting those in this equation number 3, basically you get this 6 second order differential equations. And here, basically what we can do, we can treat each second order differential equation as a subsystem. And note that here we have this control inputs U1, U2, U3 and U4. And we have 6 degrees of freedom. X, Y, Z are the translation motion and phi, theta, psi are the rotational motion. So you can see that we have 6 variables, but the control inputs are 4. That's why this system is called under-actuated system, as I had told earlier. So at a time, we will be able to control only 4 variables, right? Because we have 4 control inputs, U1, U2, U3, U4. We will see which control is responsible for controlling which parameter in the next slide. So of course, these parameters are there, M is the mass, G is the acceleration due to gravity. So just note that we have this 6 differential equation which connects 6 degrees of freedom to these 4 controllers. And those 4 controllers are basically our 4 actuators which are controlling the rotors. Okay? Yeah. So let me first briefly discuss how basically the control will happen. Then we will go to the sliding mode control design. So basically we have these 4 rotors and of course the movements will be generated by these 4 motors. So let's say that each motor rotates with the angular speed of omega 1, omega 2, omega 3 and omega 4. So one can first visualize the motion of a quad rotor from ground to a height. So when a quad rotor has to move from ground to a height, first you have to basically, for this hovering thing, the total thrust which is in the negative z direction should be equal to the rate of the quad rotor. So from there, basically you get this relationship of U1, which is U1 equals to mg, and the thrust of each rotor is represented by this Ti equals to d, and omega is the angular speed of each. So from here, one can see that the control of z variable is done through U1. So U1 is the control input responsible for the height control. And at that point, if we note the net this, so we are just right now seeing the situation when the quad rotor is hovering. So here U1 is the total thrust in the negative z direction, and U2, U3, U4 are taught about the x, y and z axis respectively. If we now look at the roll motion, the roll motion is the net movement. If you look at U2, so U2 will be something non-zero. It can be negative or positive, and depending on that value, it will either roll right or left. So you can see when the angular speed of these 2 motors are more are greater than these 2 motors, basically the quad rotor will roll right, and in the other scenario the quad rotor will roll left. And at that point the control input U3 and U4 will be 0. So we are talking about the roll motion right now, rotation around x-axis. Okay. Then if we see the rotation around y-axis, which we call as pitch, then at that time, basically the angular speed of these 2 motors will be greater than the angular speed of these 2 motors, and it will be called pitch forward, and in the other scenario, it will be called pitch backward. And again, if we look at the net movement now, so here U2 will be 0, which was responsible for the roll motion, and U3 will become either positive or negative, and accordingly we will have pitch forward or backward UC. So for rotation around z-axis, the angular speed of basically this diagonally opposite this rotors will be same, and they will be greater than this. Then the quad rotor will move in the pitch left, your left, and in the other scenario it will do your right. And in this case, your U4 will be non-zero. So what we have noticed that we have 4 control inputs. U1, which is for controlling Z, we have U2, which is for controlling roll, U3 for controlling pitch, and U4 for yaw. So what from here you can see that we are controlling the angles and the height. Okay. But if I ask you that you want the quad rotor to follow a desired trajectory, which means you have XT and YD. So in that scenario, how we will do the design? Because these control inputs are making phi to go to phi d, theta to go to theta d, and psi to go to psi d. Okay, basically that is what these controllers are doing. So what we do, we basically use the concept of virtual control over here. So we assume that there are two virtual controls, suppose UX and UI, which will make X to track XT and Y to track YD. And then we use this this thing to find the desired angles. So we have the desired trajectory. We design a virtual control so that that desired trajectory is tracked, and using those desired trajectory control inputs, we find the angles, desired angles, which will be controlled later on using U2, U3 and U4. I'll just show that in the next slide. So we have used the super twisting based sliding mode control for tracking the attitude and altitude. So altitude Z and attitude is phi theta psi. And we have also done the simulation results in the presence of different disturbance scenarios. And as now you might have already, I guess, understood that for sliding mode control, we have two design steps. First, we design the sliding surface, and then we talk about the design of sliding mode controller, which will be a stabilizing controller. So in this scenario, we have designed a PID sliding surface. And then using that PID sliding surface, we have given the control inputs, U1, U2, U3, U4, and UX, UI also. First, we have done the simulation in the MATLAB, and then we have also done software in the loop simulation of the this iris model of the quad rotor with the effect of different wind conditions, the gazebo environment. So as I have told, our objective is to design and implement a super twisting sliding mode control for tracking of a reference command in the presence of external disturbance. So we have seen those 6 second order differential equations. We can basically write all those 6 order differential equations, all those second order 6 differential equations in this form, the consolidated form using this new variable, where basically the state vector can be represented by this, which is the 12 cross 1 column vector, and the control inputs are these following. So as I was mentioning previously, that we will look at the second order differential equation as a subsystem. Okay. So if we consider the first second order differential equation, which was basically, let me just go back and show you. So yeah, if suppose I consider this equation at a time, which basically tells you the dynamics for the phi, right? Which is the role dynamics. So then we can basically design the control input U2 for making phi to go to phi d. Similarly, we can then treat this as a second subsystem, then third subsystem, and the fourth subsystem. And for the virtual control also, we will basically use this X and Y dynamics equations. Yeah, so basically this is the role subsystem, okay, where we have this states U1 and U2 as phi and phi dot, and U2 is the control input. And we have assumed a disturbance entering over here to the input channel to show the robustness of the sliding mode control. So the first step will be to define the tracking error. So first we define the tracking error as phi d minus phi, and then we have proposed a PID sliding surface where basically we have these 3 terms. Normally you would have, like if you have studied the sliding mode control, you would have seen this P and D term in the sliding mode control. Here we have also added this I term basically to reduce the steady state error. And after certain analysis, you will find these relationship between this aim, KP, KD, KI. So that is done for the asymptotic stability of the error that I'll show later. And using this sliding variable, we can come up to this control input, which basically when you substitute in the dynamics of sliding variable, it results into the super twisting structure. First, we have defined the error, then this is the sliding variable, and then this is the proposed control law. And now if we use this, as I said, this proposed control law in the dynamics of the sliding variable, you will achieve this 2 second first order differential equation. And this is nothing but the super twisting structure. Okay. And then of course we have given this gain K depending on this upper bound on the differentiation of the disturbance, and this theorem basically gives us those gain values, and this makes the variable S1 and S2 to go to 0 in finite time. And once S1 goes to 0, which means S5 goes to 0, and S5 is this variable, which means your this term equals to 0. And then after that, you can use very simple Laplace transform method, and you can see that this error will go to 0 asymptotically if you choose these gains Kp, Kd, Ki as I had mentioned previously, with the relationship between these gains. Okay. And of course, we have done the analysis, the stability analysis of the sliding variable using this Lyapunov function, which is like given by Moreno in literature. And we have come up with some different, this matrix for that case, and these are the gains. So from here, what we can see that we can design one control input mu2 for tracking phi angle. Now in the similar manner, we can basically design all other control inputs. So you can see here for theta, phi and z, for theta, psi and z also, we have given this PID sliding surface, and then accordingly we obtain these control inputs. So from here, what we have achieved, that we have a super twisting based sliding mode control U1, U2, U3, U4, which will make phi, theta, psi and z to track the desired variables in the presence of disturbance. That's what is achieved till now. Now, as I told, for tracking the desired trajectory, we will use the virtual control method. So for that, first as I told, we will assume there is a control input Ux and Uy in the system. I'll show where it is. And then assuming that, we can again give a PID sliding surface for the X and Y control. And then this is the major relationship between the virtual control Ux and Uy and the desired phi and theta. Because we have already seen how we will control phi and theta, from here what I am saying that we will design these control input Ux and Uy in such a manner that we will be able to track any desired trajectory, xd and yd, and then using that we will obtain this desired phi and theta, which will be later on controlled using u2 and u3. So if I go back again, so in this virtual technique, basically if you look at this differential equation, here x double dot equals to u1 by m, so this whole term is basically considered as ux. And over here, this whole term is considered as uy. So you can see the ux and uy control will depend on u1 also. So if you look at the expression of control input which we have obtained, so as I told, this is the ux and uy, and these are also the control input based on super twisting sliding mode control. So these are the virtual control. So using these virtual controls, we can basically find the desired phi and theta, which will be controlled using U2 and U3, which we have already seen. So this is the basic design step of the super twisting based sliding mode control for a quad rotor, both altitude and altitude control. And then we have done the MATLAB simulation, and we have used basically this 3DR iris quadcopter model because this was in the gazebo. So same basically all the model values, moment of inertia and mass we have picked from there, and in the MATLAB also we have used the same values. So this is the initial condition. And of course we have tuned all the gains. So you can see that we have gains in the sliding surface, then we have gains in the control input also. So accordingly we have chosen these values, and the desired trajectory is basically represented by this equation, which is the equation for a Lissajous curve. Okay, and here we have the maximum speed also, Vmax, which I can show in the gazebo what was the value. And for simulation, in MATLAB simulation, we have considered this disturbance, which is, you can see, differentiable and upper bounded also. Because as you might have noticed, in the super twisting algorithm, we have this constraint that the disturbance should be differentiable and the upper bound should be known. So in simulation, we have chosen this kind of disturbance in MATLAB simulation. So if we look at the plots, so these are the plots of the sliding variables, all the sliding variables. And you can see basically the sliding variables shows the finite time convergence. And accordingly, if you look at the plot of the error variables, so all the error variables are also asymptotically stable using the PID sliding surface. After that, we have done the ROS gazebo simulation in the software in the loop simulator. So this is the computer configuration we have used, and the system is simulated on PX4 firmware. So basically, this PX4 can be directly put into the Pitchfork autopilot, because we have not done the hardware of this thing, but we have only done the software in the loop simulator. So we have simulated different wind conditions. So in Gazebo, you have this wind generator plugin, by which you can basically generate different wind profiles. So we have done this Gazebo simulation with no wind, and then wind, constant wind of this value, and also we have done using this stochastic wind. So in our theory, we are not claiming that we will be able to reject the stochastic wind, because we can see that we have the condition that the disturbance should be differentiable. But about the stochastic wind, I can't say that. So in Gazebo simulation, we were just trying to look at how, like, what is the performance of our controller if we at all give this kind of disturbances. Okay. And you might have noticed that in the sliding variable and the controller, at the both places, we had the integral terms, right? So, yeah. So if you see, we have these integral terms over here, the sliding variable, and also we have this integral term in the control input, which basically gives a rise to the, give us the super twisting structure. So for Gazebo-based simulation, we have basically used exponential smoothing filter for and we have done that differentiation using discrete derivatives. Okay, to basically eliminate this high frequency noise. So this is the structure block diagram of the ROS Gazebo software. So this is the model of the quad rotor the Gazebo. Now I guess the higher version of the Gazebo has come. This work we had done in 2021, and now you have the advanced platform also. So basically we have this model over here, and using those states, we have basically generated a ROS topic on which the super twisting sliding mode controller is being calculated, and that ROS packet basically is communicated to this ROS node, and that basically goes to this PX4 flight stack using Lavalier packets, and then that basically gives the control input to the quad rotor. So here basically, because of this PX4 flight stack, we have used, normally it comes with the PID control, that you can use that mode by which the PID control will be tuned. So we have disabled that thing, and we have done the whole control ourselves. So that's why the controller which we have given is totally sliding mode based. We have not used PID control at all over here. So I would like to show this video of this in implementation. So this is basically the video from the Gazebo environment, and this is the video from the MATLAB. And here you can note that this is the Lissajous curve, and the black is the commanded trajectory, and red is the evolution with respect to time and the angle and everything you can look at here. So this is so the previously it was with the no wind condition. This is the wind condition when wind is 0 basically. So you can see that the tracking is very good, because we don't have any disturbance in the system. Now this is the simulation 2, where the maximum speed of the quad rotor we have fixed as 2 meters per second. So if you remember, this is that Vmax, and the constant wind of 3 meters per second we have applied along the positive x direction. So you can note that this curve is such that the turning at this point is more, right? And if you look at this section, it is more or less kind of linear. So if we apply a disturbance over this side, like on the x-axis, you will be able to see the deviation more good. Like if our controller is really able to, reject that disturbance or not. If we apply the wind in that direction. So that's why we have chosen the wind direction in positive X direction. Okay. Now this is the third simulation where we have chosen the wind of mean value this and the variance of this, and the maximum wind speed is 5 meters per second. Here again we have chosen the wind in the along positive X direction. So you can note that of course the quad rotor is able to deviation, but it still comes back on the trajectory. Even if it will work, but in simulation we can see that it is able to reject certain kind of disturbances which are actually not differentiable, and we are not even using the upper bound. Now I will come to the second part of my talk, which is event-triggered sliding mode control for a higher order system via reduced order model-based design. So this will be a kind of switch now, because I was talking about the application. Now it will be more theoretical. So yeah, please be with me. So now I will talk about this event-triggered implementation. So we all know with the boom of digital platform, the controller nowadays is implemented in a discrete manner. Okay, so we have the continuous controller. It is mostly implemented in a discrete manner. So what we do, we fix a sampling time and we do the implementation in the periodic manner. That is fine, right? We normally do the control implementation in the periodic manner by fixing a sampling interval. So there basically we don't look at the evolution of the state, that how states are evolving. Depending on the bandwidth of your system, you will just choose certain some sampling interval, and then we will apply the controller so that the system is stable. And we know there is a condition on the frequency should be 10 times of the frequency of the system. That condition is there. So that always met, and we basically do the periodic implementation using that key. So we can see that the controller is executed irrespective of the evolution of state. So do we really need to do that? Like suppose you have reached in a band. Okay. So when we talk about the asymptotic stability, you know that there is always a error. At the steady state, there is always an error. We also study that, that in 4t time, it will come in some steady state bound. Correct? So if your system has evolved in such a manner that state has come in that bound, do we really need to still apply the controller at each sampling time? Because there is not much evolution on the state of the system. So why don't we keep our controller constant for longer time and don't update it? So basically, which can lead to basically efficient usage of the communication channel and the resources in terms of the control computation. So of course, in the periodic implementation, we know that the difference between two consecutive triggering instant, we can call it triggering instant or control updating instant, is constant, which is X sampling period. And we can understand it through this block diagram. So we have this plant, we have the controller, and so thinking that we have all the state of the system variable, then we have a clock basically which is triggered by a sampling time, and then that closes this loop and the state of the system will be transmitted to the controller at that sampling interval. That is the periodic implementation. Okay. So we are sending the state information to the controller at every tau second, or maybe you can let me call it as at every x, 0, x, 2x, 3x. We are sending the information of the state. So as I had already told, that what can we do to have less computational burden and to have the reduced usage of communication channel? What can we do? So the answer to that will be aperiodic implementation, because we have seen that block diagram for the periodic implementation, right? So if we do aperiodic implementation, how we can basically achieve this, to aim to objective of our design. So what is the use of aperiodic implementation? Basically, in context of sensor actuator network, it will be wise to execute control as rarely as possible. This we have computed control at one point of time, and we will keep it constant. And then we will compute only when it will be necessary. we will not basically keep on computing the controller for that time being. And basically that will basically make that processor time available for the other tasks. So here we will be showing the control input of one system only, but this can be used for the parallel processing kind of thing also in the embedded system. When you have multiple tasks to execute, so you can basically give the communication channel or even the processor to different tasks in a dedicated lab. So event triggering is one of the aperiodic implementation technique which we'll be discussing. So this is the block diagram of our event triggering strategy. So here again we have the same plant and the controller. Now the state of the system will be sent to the controller only when this rule will satisfy. Okay, so you can say that okay, so when I say a rule, you can either have it something greater than 0, then basically this loop closes, or you can say that when something is less than 0, the loop is always open, it doesn't close, something like that it can be. So this rule basically can be designed using either state of the system or the output of the system. Nowadays, this was basically when I started, like I studied the Tabuda's paper, which came in 2007. And now you can see that it has evolved too much, and these rules are basically obtained using parameterized states, outputs, even input-based also rules have been proposed. So in our work, we have basically designed this triggering rule based on the states of the system. So this part is okay? Like we have the plant, and then we are sending the state information to the controller only when something is happening in the system. What is that something we will see? Okay. So we are not basically transmitting these states continuously at every X time period. So in this case, basically this triggering instance will be generated by this triggering block, which I am calling over here as rule. And the inter-event time, basically the distance between two consecutive control updating instance will be now time varying, XI. In periodic implementation, it was X, it was constant. Now in this case, it will be varying, it won't be constant. So because when your inter-event time will be bigger, then the sparsity pattern of the triggering sequence will be sparser. Means basically the triggering instance, if you will look at, that will be sparser. Suppose we start at time t equals to 0, then at next time maybe at 0.2 we are updating the control, then next we are doing it at 0.5, like that. But if I fix the sampling interval at 0.1, so at every multiple of 0.1 the control input will be updated. So here our triggering instant which we have proposed, it depends on the state trajectory. And what we have done, we have used the model order reduction based technique. So for a higher order system, we will be using reduced order model, which basically helps us in making this inter-event time bigger, making this triggering sequence more sparser. So what we have done a lower order synthesis of the controller, because for the design of controller also, we will be using the reduced order states, not the full order states. And along with that, for the triggering rule also, we will be using the states of the reduced order system. And so you can think that suppose the order of the original system is N, and the order of the reduced system is R, where R is less than N, then we are transmitting a state of lesser order. So basically that takes less communication channel bandwidth, right? So from there you can see that from the transmission point of view also, this reduced order vector based triggering rule can outperform the full order based technique. So this is the LTI system which we have considered. Over here we have taken this mass disturbance D. It's a single input case. So this is our uncertain plant whose dynamics is given over here. Then we have, so from this point to this point, basically we are finding the reduced order model over here, and then we are using the states of the reduced order model in the event triggering mechanism. And then according to that mechanism, the triggering instants are generated, and then through that the states of the reduced order model is sent to the controller. And the controller is also designed using reduced order states of the systems. And that basically stabilizes the system, the higher order system. Is that where AD is controllable, and we are also assuming that this disturbance is bounded. So as I had told over here, this is the full system. So this is the system which is nth order, which is represented by X. So this is an nth order system represented by X, and it is over here, placed over here, this uncertain plan. Now, we have used this aggregation method to find the reduced order model of the system. So using this aggregation method, basically there exists this transformation matrix P, which transform this state X to Z. So this is our transformed system in Z coordinates. And over here, basically Z has two components, Z1 and Z2, where Z1 denotes the states of the reduced order system, which is the dominant system. So how we are basically reducing the system from higher order to the lower order, we are assuming that there are some dominant modes and there are some non-dominant modes. So the dominant modes will be kept to obtain the reduced order system, and this Z2 will basically represent the non-dominant modes of the system. So then basically our transformed system Z can be thought of as these two subsystems, where Z1 is equals to, Z1 dot is equals to this, and this basically denotes the reduced order model, which contains the dominant modes. And this Z2 dynamics is here, which is the non-dominant modes of the system. And this matrix CA bar, which is called as aggregation matrix, it basically gives a relationship between the dominant mode of the system and the full order system states X. Okay, so the full order system state X is related to this Z1, which is the state of reduced order model, using this matrix CA bar, which is called aggregation matrix. After that, so basically we have obtained these two models from the original system. So this is the original system. Then we transformed into this model, and after that we divided it into dominant and non-dominant. Now, after that, in this one approach, so we have also done the same kind of analysis without transforming this system into the regular form. Over here, what we are doing, we are transforming the reduced order model in the regular form. So in the regular form, basically, we have the input matrix in the form of 0, 0, 1 or 0, 0 identity, if it's a multi-input piece. Okay, so that is the regular form structure. So here, basically, using this W transformation, so you can see over here W. So W1 and W2. So this W1 is basically responsible for transforming the reduced order model, which is represented using Z1, into the regular form. And then W2 you can see is identity only, so that remains same. So this Zn is nothing but Z2 only, but this Zr dot now is in terms of this regular form. So when I say regular form, you can look at here that this D12 will be 1 in case of single input case. So we are able to write the system model in this 0001 form. Okay, so this is the regular form. So after we obtain this regular form, now we have proposed the sliding variable using the state of reduced order system. So here SZ is found using state of the reduced order system, ZR, in the regular form. Okay. So just to remind, initially we had X, then we transformed into Z, which had two components, Z1 and Z2. Now Z1 is transformed into ZR, and ZR is basically reduced order system in regular form, ZR. Okay. So this is our sliding variable design using these states, where the sliding parameter is chosen accordingly. Now this is the sliding manifold. So in event triggering mechanism, basically this is the control input which we have proposed. So suppose if it was not an event triggering mechanism, it was a continuous control technique, then you would have over here ZR of T, SZ of T. Basically, the control will be computed as T progresses. Okay. But here you can note that ut. So the value of this control input u at a time t, where t is fixed in this interval. Okay, it is closed at t1 and it is open at ti plus 1. Sorry, not t1, ti. So from ti to ti plus 1, this control input ut will be computed using this relationship. And over here you can see we are using the value of state at ti, which is the current time, ti. So if I say I am starting the system evolution at t equals to 0, so this ti is nothing but 0. So at that point, u of 0 will be calculated using initial condition of zr, and sz will of course will be calculated over here, and similarly this. So this u of t for time from 0 to t1 will remain constant, this value. Now how this t1 will come? This t1 will come depending on some triggering sequence, depending on some, violation of the event, so which I will show later, and these are the control gains. So what is that triggering rule? So we basically define this error, which we also call as sampling error, Ez of t, as difference between the state value at current time minus zr with t. Means from t basically where varies from ti to ti plus 1. So at ti, so you can see this is definition of this error for time interval ti to ti plus 1. So at ti value, Ez of ti basically becomes 0. So at every ti, this error is made 0. And then this error increases to certain value, then again it becomes 0. So the definition of this error, you can note, is done in such a manner that depending on certain bound, on of course basically this variable, this difference, the error will be 0, then it will increase, then it will again come to 0, then it will increase. Now this increment, that till what point it will increase, will depend on the triggering condition. So the triggering condition which we have proposed is this. So at t0 we assume that controller will be implemented at t0 equals to 0, and then the further triggering instance will be calculated using this condition. So whenever this error, which is over here, so whenever this error becomes greater than equals to sigma delta, the next triggering instance will be generated. So initially this error will be 0, then we will let it evolve until it reaches this value, sigma, and then t1 will be generated. So at that point of time, we will calculate the control input using the state at t1. Then again we will let this error grow. As soon as it reaches sigma alpha, again the t2 will be generated. So like that, this triggering instance will be generated, which will help us in maintaining a bound on this error. So here alpha we call as the triggering parameter, and sigma is chosen between 0 and 1. So you can think of this sigma as a parameter which basically used to tighten this condition. Okay, it is between 0 and 1. So in the worst case scenario, you can see we are triggering a bit before on. We are not letting it reach exactly alpha sigma value. We are triggering it just before that by introducing this term sigma. So in our proposal, as I told, we are using reduced order states. So if we had done the same thing for the design of event triggered control for the full system, we might have used this error. So this error is basically using the full state of the system. Right now you can note that ET is depending on ZR and Zn state, which are the state of the full system in the transform domain. And here Ez is using only the reduced states of the system. So these two, you can see that this is the difference over here in these two errors. So this error, this sampling error is for the event triggered implementation of the control designed using full state of the system. This error is for the event triggered implementation of the system using control design using reduced order state of the system. So from here only we will be able to look at how basically we are able to achieve a sparser sampling pattern. So you can note that you can note this relationship. So this can be seen very easily that norm of ET square will be nothing but norm of this vector plus norm of this, depends in this. And a norm of this will be nothing but Ez, norm of Ez square. So this is what written over here. Using the norm property, you can write this relationship. So from here you can note, suppose we are at a time where Sj and Ti. So Ti are the triggering instants generated using this triggering rule. Triggering rule using reduced order split. Okay, triggering rule using reduced order split. That is using Ez. So Ti are the triggering instants generated using this rule, and SIs you can say are the triggering rule generated using this triggering condition. Okay, where instead of using Ez, we will use E. That whenever norm of E is greater than equal to this value, we will trigger. So you can see that of course from the design itself that the norm of this error will be greater than or equal to norm of this. Why? Because this E contains this and in addition to that some more variables. Is it okay? So you can look at that from here. So if there is a time when this becomes, this becomes equal. So you have, that's what we have written over here. If suppose this is the time instant when ZR of SI is equals to ZR of TI, basically you can see that over here this term will dominate this term, which means that this condition will be violated more frequently as compared to this. Why? Because the value of this error, the norm of this error will be greater than equal to norm of this error, which basically makes the triggering instance generated using this rule more frequent as compared to the triggering instance generated using this. So basically from that we can say that the triggering instance which is generated using reduced order based mechanism will be giving the Ti plus 1 greater than equal to Sj plus 1. So from here, if I say that at t equals to 0, it was same, means t equals to 0, this condition was satisfying, then the next T1 which will be generated will be greater than S1. So there will be 0, S1, T1. Because S1 is found using this rule, norm of E2, which has bigger magnitude as compared to this. Okay. So from here, basically we are able to achieve a larger inter-event time using the reduced order based design as compared to the full order based design. So having said that, then in sliding mode, you might have heard the term quasi-sliding mode in the discrete domain. In discrete domain, we are not able to achieve the ideal sliding because there is a sampling time at which the control is implemented. So in the event-triggered implementation, we introduce this definition which is practical sliding mode. So in the continuous implementation, at least in theory, we can say that sliding variable becomes 0 in finite time, and the states basically slide on that s equals to 0. Okay, but in event-triggered scenario, as we are letting the error to grow, as you can see the condition which we are using as the triggering rule, we are letting error to grow. So because of that, we are basically kind of introducing a band around the sliding variable, and that band basically we are calling as practical sliding mode band. So we have, so for every epsilon greater than 0, we will be able to find a tau z such that the sliding variable will satisfy this condition after the finite time. So in continuous domain, we say that s becomes 0 in this finite time. But here in event triggered implementation, we say that this s will be less than equal to this quantity after a finite time. So now so this is the stability proof. I will just give this idea what we have done. So what we have done, we have defined these two sets. So one set is for the state of the system and other set is for the sliding variable. And the initial condition of this variables will be chosen such that they lie in this set. And then using that set definition, basically we prove that the states of the system will basically converge. So I'll just briefly tell this, that suppose so we have omega 1 set for ZR1 and omega 2 set for SZ. So this is the omega 2 set, okay. So you can say that suppose somewhere over here we will have S equals to 0 line. S equals to 0 line, and then you have this lines at the both sides of S equals to 0. So the initial condition of this ZR1 will start in the omega 1 set, and it will basically remain in this omega 1, and SZ will also remain in omega 2 if this condition is satisfied. Means the initial conditions will be chosen such that this condition is satisfied. After that, this is the theorem basically which gives us the finite time practical stability of the sliding variable and then the stability of the states of the system. So I'll just skip it in the interest of time. You can refer to our paper for this. So we basically prove that by choosing the switching gain in this manner. So one thing I will just like to highlight here, the switching gain which was over here. Yeah, so this is the switching gain KR. So you might have, if you have studied that this in continuous sliding mode, this switching gain depends on the upper bound of the disturbance. In this scenario, in addition to that, this KR also depend on the triggering parameter. The triggering parameter which is basically over here, this alpha and sigma, the triggering gain. So this is the proposed control gain KR, and this term is because of the triggering rule, and this term is the as usual which depends on the upper bound of the disturbance. So basically by choosing the control gain like that, we will be able to prove the practical stability of the system. So for simulation, we have considered this fourth order system, okay, and this is the disturbance we have considered. So the eigen values of this open loop system, if you check, are these 4 values. And then we have basically neglected these 2 non-dominant poles because these are very far from the origin, right? So we have considered these 2 eigenvalues as the dominant modes, and this is the reduced order system obtained by considering these 2 as the dominant mode. And then according to our proposal, these are the other variables chosen. And we can see that now the states of the system evolution, that it is bounded in a set. So of course, this depends on the value of epsilon which we have chosen. So if you remember, SZ, mod of SZ is less than epsilon. So you choose a epsilon beforehand, and depending on that epsilon, your triggering conditions will be generated. So in our case, we have chosen epsilon equal to this value. Okay, and accordingly the other parameters are obtained. And this is the evolution of the sliding variable. So you can see that starting from one initial condition, the sliding variable is entering into this band in finite time, and it remains over there. So this, we have not plotted this value, but this value will be nothing but 0.00994, which was in the definition of practical sliding mode also. And this is the evolution of control input with respect to time. So you can see that as we are keeping control constant for some time until the triggering condition is not violated, so we have this kind of motion. If I zoom in, you will be able to see that control input is kept constant, then updated, kept constant, and then updated. And same thing can be seen from this plot of inter-event time with respect to time also. So this is the TI. So you can see that the TI, which is the difference between 2 consecutive triggering instant, takes value, over this whole spectrum. You can see that from starting from this to this value, it varies. So depending on how the states of the system is evolving, we are basically able to obtain the triggering instance at which the control input is calculated. And what we had done that for comparison, we had compared it with the periodic implementation. So we kept we kept this bound constant. So we wanted to achieve this same bound using periodic implementation, and using event-triggered implementation. So for achieving this same bound, the sampling interval which we obtained was 0.05 in the periodic implementation. So for using this, by using this 0.05 second, basically we were finding the control instance 400 times more in the case of periodic implementation as compared to the event-triggered implementation. So we basically say that we are able to reduce the calculation of control over here using the event-triggered implementation as compared to the periodic implementation. So I'll maybe skip this. So the same thing we have done for the discrete time case also. So this was done in the continuous time. In case of discrete system, basically now the triggering instance will be some multiple of the sampling interval. In continuous case, it was time varying, some 0, T1, T2, and there is no basically relationship between these inter-event time. In case of discrete time case, basically it will be some 0, tau, 3 tau, 5 tau. The triggering instant will basically be multiples of this sampling interval. Okay, so because otherwise it will implement at 0, tau, 2 tau like that. So yeah, so I'll skip this. In discrete domain, we have used Bartholdi's reaching law for designing the control input, and this is the triggering mechanism we had proposed in this case. Here also it depends on the error, which is defined in this manner, very similar. So I'll just skip this part. Okay, so over here you can see in case of discrete time system, the sampling interval was chosen as 0.01. So discrete system is at sampling interval 0.01. Using event-triggered mechanism, the control input are applied at multiple of it, which is 0.02, 0.03, and 0.04. And this is obtained by fixing this bound. Basically, we have fixed this sliding mode band, and accordingly, we are obtaining these triggering instruments. So now I'll just give a very brief overview of the work going in our lab at ISC. So basically we have certain system developed at Control and Robotics Lab at the Electrical Engineering Department at ISC. So we have made these robots in-house. So this is a 4-wheel differential drive robot which is developed using Raspberry Pi Pico W, and it basically follow this unicycle model. Then we have also developed this omnidirectional robot using the Omni wheel and the again Raspberry Pi Pico W. So the good thing is that we have used same PCB in the both robotic design, and this omnidirectional robot basically follow the single integrator model. Then for the feedback, for the localization of this system, basically we have developed this camera-based localization system. We are using this one wide-angle lens camera on the ceiling, and then we have put this markers, which is called Arupo markers, on each of the robot, and then basically using the Wi-Fi router, the communication is happening between our workstation and the robot. So in the workstation, basically we are running a image processing code and the multi-robot controller, and the operating system is Ubuntu, and we are using this ROS Humble Hubsville version. And then using computer vision library, which is using OpenCV, we are able to do this image processing, which basically takes this Arupo markers and then give the position of each robot in the localization system. So this camera is basically connected to the workstation using USB, and this camera takes the video information, and using this image processing code, we are able to send the data back to the robot. So I'll just show this small video of the experiments we have done with these robots. This is just to show the development. We have not used any advanced control yet. These were to check the capabilities of our robot which we have developed. So we can see this was in the previous video. It was doing the obstacle avoidance. So we have written very ad hoc code for that. So the static one is the omnidirectional robot, and the 4-wheel differential drive robot was able to basically reject to the obstacle avoidance. In this case, this omnidirectional robot, so as I told, it follows the single integrator dynamics. So we are able to control X and Y position and the theta also. And then now you can see the same robot is doing the Lissajous curve, this infinity curve over here. Then we have done this multiple robot implementation also. So here we have these 4 robots. So initially they go to an initial position. So we basically divide the orbit, either it's a circular orbit, Lissajous curve or ellipse. We divide that equally among the agent so that they reach to the initial condition. And after that, basically they do the desired reference trajectory tracking. Now this is for the elliptical orbit using the four robots. And this is the Lissajous curve tracking, which was, it is very similar to one I had shown using the quadrotor also. So here also, they are able to do the obstacle avoidance because we are giving them the collision avoidance in the control, but we are putting them in the initial condition so that they don't collide from the starting itself. Then in this, basically, you can see the middle robot is doing a circular orbit tracking, and then these 4 robots are basically surrounding that and still moving in that circular way. So here, this is the omnidirectional robot, and these are the 4-wheel differential robot. So the kind of, yeah. So I will now end my talk. So currently, basically, we are also trying to do this adaptive based law for the quadrotor and even also for the ground robots. And we want to do this control of multi-quadrotor system for the application in agriculture. So we are looking at that. Then, as I was telling, this event triggering can be used to divide this, communication channel in among different tasks. So we are basically looking at that how can be used in the multi-quadrotor system. How that when they need to communicate, do they need to communicate all the time or not? So these are some of the feature work we are looking at. Right now we are able to develop the system. Now we will go towards the this control design and the hardware. So yeah, these are the references, and thank you.
Long live India and France friendship.